All right, so chapter 8 in our textbook is entitled confidence intervals, and we're going to talk more about those. But first, section 1 is for when we know the standard deviation. All right, and the purpose is, and you can read, but I'll go ahead and read it. It says to estimate the value of an unknown population when sigma of the population is known. So when the standard deviation of the population is known. So we have this definition of what a point estimate is. It's when we just take a sample and we presume it goes to the entire population. So here's my example. The average age of CSU Stanislaus students, let's say we take a sample of 100 students and we find that our average is 22.3 years old. So we basically would say that, all right, well, then based off our sample size, and we're going to say about the average age of CSU Stanislaus students is 22.3 years old, which may or may not be true, but as the sample size grows, then we're able to be more accurate. But for right now, a point estimate, the sample mean is the best estimate that we have. Then there's an interval estimate. This is what we're going to be working with mostly. You can see I've highlighted some important parts. So what we talk about a range of things. So where will our average fall? And that's what the confidence interval does. And you can see I've circled it and bolded it into red over here. So what we say is we say that the average is between two values. So let's say an interval estimate for the average age of CSU Stanislaus students might be 21.9 to 22.7. Okay, so we're going to say that the average lies between that. And we could also write it as 22.3 because that's what we originally said. And we could say it's plus or minus 0.4 years. And you're going to see how we come up with this. We're going to get into that. Then the other thing is we say that we are confident. We have a confident level. If we say we're 95% confident the average will be in the interval, right? As the percentage it goes down, our range becomes more. Okay, if we want a 99% confident, then our interval will need to be widened. So if we're 95% confident, then it's more narrow, no big deal. But if we're 99% confident, then we want to make sure it really is in there. So this would be an example of being 95% confident. You can see that we go from 21.9 to 22.7. 99% confident would be 21.7 to 22.9. See how it's widened by 0.2 years on both sides? But again, this is nothing that you know how to find yet. We're going to get into that. Now, the next is common confidence intervals. We have 3 common intervals that we use, and we use 90%, 95%, and 99%. These are the most commonly these are the most common ones that you will see. So there is a sweet formula here for alpha when our average is known. So here it says that we have our x bar, which is our sample mean, and we have our critical value, which is here, and we're going to be using our table. And it says alpha is the total area of both tails. So we might say our alpha is a certain percentage. And then alpha over 2 is the area between 2 tails. Now look, this right here, you're going to want to memorize, write it down. You can just know this. You don't even have to use the table, all right, because these are the ones that we're going to be using. But 90% confidence interval gives you a 1.65 for your z-value. A 95% for your z-value gives you 1.96, and a 99% gives you a z-value of 2.58. All right, moving on. So here's a visual here. Our visual, if I set a 95% confidence interval, well, this is 95%, so this is going to lie in here somewhere. All right, the 0.5% goes here, and it comes out here because 95% plus 5% is 100. But the thing is, we have 2 sides to this. We have one side here, and we have one side here. So if I take 0.05 and divide it by 2, that gives us 0.025 on both sides. All right, so one more thing before we get into our first example, a rounding rule. We round to 1 more decimal place than the number of decimal places in the original data. So if we're given in the original data a bunch of whole numbers, you're going to see that the average, standard deviation, and so forth will be rounded to 1 more decimal place. If we're given something with the 10, so it's like 20.2 or 40.6, then we're going to round to one more decimal place to the hundredths. And you'll see by example here. All right, first example. A researcher wishes to estimate the number of days it takes an automobile dealer to sell a Chevy car. A random sample of 50 cars had a mean time on the dealer's lot of 54 days. Assume the population standard deviation to be 6 days. Find the best point estimate of the population mean and the 95% confidence interval of the population mean. So we have some things that we know. So first off, if you look back at our formula here, we need to know our average, our mean, our standard deviation, our sample size, and then what our X bar is. So there's 4 things we need to know. And just notice that it's almost identical to this side, but this one we're subtracting, this one we're adding, because we're getting the lower bound and the upper bound. So there's 4 things we need to look for. So first, let's read it. The first just kind of tells our general idea. Next says a random sample of 50 cars. This is our population size, so this is our N. Next, it says had a mean time on the dealer's lot of 54 days. This is our X bar. It's the average time, the mean time that sits on the lot. The population standard deviation is 6 days. So right here is your sigma. And then lastly, the 95% confidence interval tells you, if you remember, it was 1.96. So what we do now is we go and we just substitute these values into our formula. So our formula, and I'll write it all out just so you can see it all. So we have X bar minus our Z alpha sub alpha over 2 times sigma over the square root of N less than mu less than X bar plus Z sub alpha over 2 times sigma over the square root of N. And the big difference is subtract addition because we have lower bound, upper bound. So our X bars, our average was 54 days, so 54. Our Z sub alpha over 2 is what we had for our confidence interval, which was 1.96. Our sigma was 6 days, so 6.0, so we just leave it as 6. Divided by our average, not our average, I'm sorry, our sample size, which was 50 cars. And then it's almost a repeat, except for it is addition. And then next we go to our calculator. So we're going to put this into our calculator and rely on it. But we want to write the step, so then it helps us see exactly what we're adding, subtracting to both sides. So we're going to continue to write 54 minus, if you put in 1.96 times 6 divided by the square root of 50, then you get 1.7. And since this is identical to this, you could put it in the calculator again just to make sure you are correct, but that will also give you 1.7. And then lastly, 54 minus 1.7 is 52.3. And then 54 plus 1.7 is 55.7. Or we could write it as 54 plus or minus 1.7. Doesn't matter which way you write it. But what does it mean? So it talks about we're 95% confident that the car will sit on the lot on an average between 52.3 days and 55.7 days. Even though I know it's hard to think of, how do you have a 52.3 day and 55.7? There are hours in the day and you could divide that. So this completely makes sense. All right, example 2 says a large urgent care center with 4 doctors found they can see an average of 18 patients per hour. Assume the standard deviation is 3.2. A random sample of 42 hours was selected and find the 99% confidence interval of the mean. So remember, we have 4 things to find. And we're just going to start reading it. So 4 doctors doesn't really help us with anything, but the average they see it per hour is 18. So this is our X bar. Our standard deviation, it gives it to us, is 3.2. Our sample is n, which is 42 hours. And then our confidence interval, which is 99%, gives us 2.58. And from that, we just go right back to our formula, and we just start substituting these values in. So we have x bar minus z sub alpha over 2 times sigma over the square root of n, less than mu. And then it's a repeat, but this one, our upper bound is adding. X bar is 18. Our confidence interval gives us a 2.58. Sigma is 3.2, our standard deviation, divided by the square root of 42. That's our sample size. And then repeat with addition for our upper bound. Handy dandy calculator right there. This gives you 18 minus 1.3, which means 18 plus 1.3. This gives you 16.7, less than mu, less than 19.3. But you have to think about, the average talks about the number of patients they see. Again, it says per hour. So can you see 16.7 patients or 19.3 patients? That's not possible, right? We could say they see on average, the average would be between 16.7 and 19.3 patients per hour if we're talking about an average. But if we're actually talking about people, we cannot have a 16.7 people. So what you have to think of is you have to go maybe a little above. Well, does 16 fit in this bound here? Does the value 16 lie between here? And the answer to that is no. But does 17? Yeah. So we're going to change this to 17. And 19.3, well, if I go above, that's 20. Well, 20 is way out here. It doesn't lie in between here. But 19 does. So we're going to say 19. So we are 99% confident that the average number of patients they will see in an hour is either 17, 18, or 19. That's another way of saying it. You do not need to change your values unless you have a context that you need it to make sense with whole numbers or a certain type of number. Money, same thing, right? Money, if we're doing a problem with money, it's usually going to give us 3 decimal places. Well, we don't deal with money to 3 decimal places, only to 2. So you'll rewrite it with 2 decimal places. All right, one last example before we move to the next section. So this example says the following data represent a random sample of the assets and millions of dollars of 30 credit unions in southwestern Pennsylvania. Assume the population standard deviation is 14.405 and find the 90% confidence interval of the mean. So 30, this should tell us our N. The 14.405 is our sigma, our standard deviation. The 90% confidence interval, it's a 1.65. What does it not give us? It does not give us our average. How do we find an average? Add them all up, divide by the total number you have. It's that simple. So if you were to put it to a calculator, you get x bar equals 11.091. Okay, so that is your x bar. Okay, next, write our formula. X bar minus z sub alpha over 2, sigma divided by square root of n, less than mu, less than x bar, plus z sub alpha over 2, sigma square root of n. Our x bar is 11.091. Oh, and I want you to notice too, remember, this is what I was saying, one more decimal place than you originally had. Notice how they have 2 decimal places. Not one has anything more. I can go through every single one and see that they all have 2. Now, someone could have had 1, no big deal. But the most I have is 2, so that means I need to go 1 more. And that's why I went to 3 decimal places to the thousandths. So 11.01 minus 1.65 times 14.405. And notice too how it gives you the standard deviation to 3 decimal places. The square root of 30 less than mu less than 11.091 minus 1.65 times 14.405 divided by the square root of 30. Calculator portion, 11.091 minus 4.339 less than mu less than 11.091. Sorry, this would be plus 4.339. 6.752 less than mu less than our 15.430. So next, you have, what does this mean? This means that the average of what they have, remember it's talking about banks, credit unions, of what their assets are in millions of dollars. The average will be between 6.752 million and 15.430 million. Or you could say 6,752,000 and between 15,430,000. We could also have written like this, 11.091 plus or minus 4.339. Doesn't matter which way you write it. All right, so the next section is when sigma is unknown. You do not know the standard deviation. So let's talk about the difference between the two sections. Section 1 is we know the value of the standard deviation of the population. And so we use the z-value table, which is on page 607 of our textbook. Or we go to section 2, now what we're going to talk about is we don't know the standard deviation of the population. So we use S, which is the standard deviation of the sample. So the difference is population means the whole thing, and the sample is we're taking just a sample size. And we're going to use the t value, which is the table on page 608 and 609. All right, so we have something called degrees of freedom. And the degrees of freedom basically is saying that if I have so many pieces of my sample, they can do whatever they want until I get this range of where I need to know what I have going on. And so you have your degrees of freedom is n is your sample size minus 1. All right. And the reason why we say minus 1 is because every value has freedom to roam except for 1. So we say how many of them are free to roam and to be whatever they want to be. Okay, or whatever it might be. But if I know the average is this, or if I know that the standard deviation is this, then I know that this one has to be this. All right. So the idea, though, is degrees of freedom is your sample size minus 1. Here's example 4. Find your t value, your t sub alpha over 2 value for a 95% confidence interval when the sample size is 22. So first off, you have to determine what your degrees of freedom is. Your degrees of freedom is n minus 1, which in our case is 22 minus 1, which is 21. So we know that we are looking at 21, which is over here. This is the row that we are looking at. Now, I know it says 95% confidence, so you would say that's a 0.95. Which if you look at our chart from before, what's left over is a 0.05. But remember, we are splitting this. So what is half of this is 0.025. So this is where we look in this column right there, the 0.025. And so what we're going to do is we look down this column, and then where they intersect, this is what our value would be for the 95% confidence interval with the sample size of 22. So it's not as easy as memorizing like your z values are. You have to actually go to your table to find it. With this also comes another formula, but the formula is incredibly simple. The main difference, this is now T instead of Z. And then instead of sigma, it's S for our sample standard deviation. All right, so example 5. Example 5 says a random sample of high temperatures for 12 recent Thanksgiving days had an average of 42 degrees Fahrenheit. Assume the variable is normally distributed and the standard deviation of the sample temperature was 8 degrees Fahrenheit. Find the 95% confidence interval of the population mean for the temperatures. So notice what we have. We have that the 12 is our N. I'll change my color back. This is our N. An average, this is our X bar, right? Our 42 degrees. Our 8 degrees was our standard deviation. So remember, now it's S for our sample standard deviation. And then the 95% confidence interval, if you can recall, what we need to do first is our degrees of freedom. Degrees of freedom is our sample size minus 1. In this case, it's 12 minus 1, which is 11. So we know that we're going to look at the row of 11. And then next, what we're going to do is we're going to look at the 95%, which if you recall, 95%, what's left is 0.05. We take that by 2 and 0.025, which gives us this row right here, or this column, sorry. So our T value, our T sub alpha over 2 equals this 2.201. So there's our fourth value that we need in order to find our confidence interval. There we go. So we have X bar minus T sub alpha over 2 times S over the square root of N less than mu less than X bar plus T sub alpha over 2 times S over the square root of N. Substitute my values. 42 minus 2.201 times 8 over the square root of 12 less than mu less than 42 plus 2.201 times 8 over the square root of 12. Calculator portion right here. 42 minus 5.08 less than mu less than 42 plus 5.08. I have 36.92 less than mu less than 47.08, or you could say 42 plus or minus 5.08. So with this, now we have a 95% confidence interval that the population mean for the temperatures will be between 36.92 degrees Fahrenheit and 47.08 degrees Fahrenheit. Last example here. Our last sample says the data represent a random sample of the number of home fires started by candles for the past several years. Data are from the National Fire Protection Association. This is real data. The sample standard deviation is 1610.3 by the 99% confidence interval for the mean number of home fires started by candles each year. So we have, this is our sample standard deviation. We don't know our N, but we do because it talks about 1, 2, 3, 4, 5, 6, 7. So our N is 7 because there are 7 values. We know our average too because we can add all 7 of those together and divide by 7. And that gives us 7041.4. And then last, we need to find what our T value is going to be. So we have degrees of freedom. Again, it's N minus 1. Our N is 7, so 7 minus 1, which is 6. So we know we're going to go over here at 6. I know this is kind of difficult, so I'm going to zoom in a little bit. So 6 is right here. Sorry, it's way too large. And we know that we have a 99% confidence interval. So if we have 99%, we're left with 0.01%. Divide that by 2, and you get 0.005. This is what we're looking for, which is going to be that column right there. So our t value is this 3.707. Here is our fourth value. Go to our awesome formula. We're going to plug in our values. Our X bar was 7041.4. Our T value was 3.707. S is 1610.3 for our standard deviation, our sample standard deviation, divided by the square root of our sample size, which was 7, less than mu, less than 7041.4 minus 3.707 times 1610.3 divided by the square root of 7. Calculator here. So 7041.4 minus 2256.2 less than mu, less than 7041.4. Oh, sorry, that should be a plus 2256.2. Subtract, and you get 4785.2 less than mu, less than 9297.6. Or we could say 7041.4 plus or minus 2256.2. What does this mean? If you look back, it says, remember, this is the 99% confidence interval for the mean number of home fires started by candles each year. So we would say that the successive years, the number of home fires started by candles, the average number will be between 4,785.2 homes and 9,297.6 homes. And we could even justify this and move the numbers differently. We could say between 4,786 homes and between that number and 92,097 homes. So we can change it to whole numbers to say that it is an actual home. It's one fire.